Hello and welcome to The Interface, the Hindus podcast to make sense of the accelerating pace of change underpinned by technology. I'm your host John Xavier, the Hindu's technology editor. Making machines intelligent has been the pastime for many inventors for ages. But it's only Alan Turing who brought a method to the way to test machines. And since then, the race to catch up with machines has been an ongoing affair. But 7 decades later, after Alan Turing started his test, no machine or complex algorithm has mastered or beat Alan Turing's test. But signs are emerging that machine intelligence could surpass human intelligence at some point of time. Will ours be the generation that sees this trend happening? Joining me to discuss this idea is Dr. Anima Anandkumar. Dr. Anima Anandkumar is the Bren Professor for Computing and Mathematical Sciences at the California Institute of Technology. Earlier, she was the Director of AI at NVIDIA. And prior to that, she was with AWS as their Principal Scientists. Dr. Anima's research focuses on non-convex optimization and higher dimensional statistics. She does a lot of large-scale machine learning optimization. So she's the right person to discuss the whole topic here. Dr. Anima, welcome to The Interface.
Yeah. Thank you, John, and great to be here and great to do this while coming back to IIT Madras. 20 years since I graduated, so it's just such a special occasion.
Yeah, thank you so much for making the time for us. So you've had this journey starting from 2004, I would say, when you started off away from IIT. So you have journeyed through the whole process. While people are just getting used to the AI wave, you have seen it from behind the scenes. You've seen it developing as a mathematician and then an AI scientist. So could you give a sense of how this whole technological curve has kind of developed and where have we come from the time you started?
Yeah. Absolutely. When I was here at IIT Madras, my undergraduate thesis was on iris recognition, like using that for biometrics and what are the signal processing tools to make that happen. And indeed, there was a lot of principles you could use to design and hand engineer what should be the right way to do computer vision for those kind of tasks. But the challenge was always that they didn't work that well at scale. And fast forward now, we have computer vision solved with deep learning, where we are learning the features from data itself. And that was the first big inflection point that happened around 2010, where instead of humans thinking about what are the right features to design into an algorithm, for instance, to recognize faces or other kinds of computer vision tasks, can we teach the algorithm from data itself what the right features are? And neural networks are flexible enough to learn features from data. And for the first time in 2010, neural networks were able to beat other traditional methods in computer vision. And the reason that happened then was both data, right? So we have internet scale data sets that were beginning to be formed. ImageNet was the first one. That was more than 1 million examples of images, and with human annotation. So humans labeling what is in an image, you had that data available for machines to learn. And the other key development is GPUs. Of course, NVIDIA GPUs are now everywhere in the news. But back then, that was the first time you could run large enough neural networks with GPUs that you couldn't do with traditional computing like CPUs, right? So data and compute were really important to make neural networks succeed. And if you see now the other inflection point that happened in late 22 when ChatGPT was released and the broader public directly interacted with AI, even though they were kind of like seeing AI systems earlier, like face recognition in airport or on your phone, it was much more kind of limited, right? It was a narrow domain model. You just didn't have that notion of continuous interaction like in a chatbot that ChatGPT was able to do. And so that was another big aha moment, because you could really see that this AI system is able to understand at least most of the times, the prompts or the instructions that you're giving to the model and responding in an appropriate fashion, not necessarily always accurate, but at least coming up with a reasonable response. And that was, again, a big change from the earlier models, which were narrow, and also what we call generative AI. So AI went from just being discriminative, meaning you're given an image and you're able to recognize what's in an image, to one that is generative, where you're able to generate a new image from scratch. And that was this step change where you could generate images, you could generate text. ChatGPT was earlier just a text model. Now we can also do both image and text. And that aspect of generative AI is where a lot of interesting applications lie, because we are now asking about a model that can really understand very broad areas, right? So like you can have text models to write pieces of software code, as well as tell jokes, as well as generate images. So that's been an exciting development.
Right.
But I still think we're early in the journey. You talked about whether beating the humans in their intelligence. And in certain ways, these models are still far from that. Because if you look at common sense reasoning, how we are able to kind of like, even if you've never seen a certain fact before, you could easily kind of like reason about it. And these models are quite limited in their mathematical reasoning and can hallucinate and make mistakes and still be very confident even when they're wrong. Yeah. And but I think there are tools to solve some of that. We've been working on how we can make these AI models prove mathematical theorems while also ensuring 100% accuracy. So really removing all of the hallucination in these models for a specific task like mathematical theorem proving. Right. The other important shortcoming in these models is their inability to understand the physical world. Right. So if you think about asking the model how to play tennis, sure, it may come up with paragraphs and paragraphs of instructions of how to play it, but it can't predict what is the exact force needed and how to place the ball and all of that, the actual act of playing a tennis. Whereas humans have that intuitive physics and can do these kind of like tasks in the real world, which still robotics currently suffer from. So text is not enough just to kind of come up with ways to interact with the physical world. Right. And there's also the world that is not just observable to us or what humans are good at. There's the whole world that is hidden from us. So if you think all the way from molecular level, how do molecules interact with one another? How do proteins fold and change their structures? That underlies everything from being able to discover better medicinal drugs to understanding like the genetic origin of many diseases. And if you go to like processes at the planetary scale, like what is the weather going to be tomorrow? Will there be a hurricane? What is the impact it has on human lives? That's also physical processes. But these are things currently AI models like ChatGPT are not able to understand because they're only based on text and some images.
It's very interesting that you brought up this whole idea of the physical dimension that the AI is unable to recognize. Yeah. Is that also the reason why when some of the generative images that come out of these diffusion models, you can't see good number of each hand has like about 6-7 fingers, and sometimes you have people just missing in a video.
Yes.
That is the reason why. Yeah. Okay.
That's one of the bases, right? So because it's only learning from data, and it has seen like fingers in many different configurations, but it doesn't know the rule that it's always just 5, or at least most of the time it's just 5, right? For humans. So that aspect of it hasn't kind of inculcated it fully. And so it doesn't have that physical validity. And you see that even more starkly if you ask it to come up with a new design of an aircraft or a drone. I mean, it may do something very fabulous. It can be aesthetically very pleasing, but it most likely won't be a drone that would fly well in the physical world. So that aspect of really understanding the physical world and designing, whether it's new drones or aircrafts or new medical devices, new drugs for the physical world, to work in this real world, we need something more. And that's actually some of the aspects
so it
I'm
still
working
lacks,
on.
if it would it be right to say that it still lacks the idea like humans have in terms of prospecting the future. It goes based on the inputs that it already has, and based on that it can generate something new, but by itself it cannot create something totally original. Is something that is very different from what we humans kind of understand as reality. Would that be a right way to
I would say that that's not entirely true, because these models can come up with very interesting new ideas, right? So they can, propose new drug molecules. They can propose new aircraft designs. In fact, if you go and search for it, like look for in ChatGPT a new aircraft design, it could be very different from what is currently being a practical one. But the aspect is it's not practical, most likely, right? Because it's more done that with an aesthetic quality, because it's seen all kinds of examples and trying to mix and match different parts of an aircraft body to come up with new ones. But it doesn't know whether that's a good idea.
Right.
So it's very creative, but it doesn't know if those creative ideas are any good. That's the missing piece.
So it doesn't know, possibly because is it also the case, because when we speak about generative adversarial networks, we also say that one segment is pushing out something positive, the other one is keeping on saying, no, this is not right. So it goes back to the drawing board and then giving out something new to us. Is a simple kind of understanding of generative AI systems.
Yeah.
But is that also because of the limits of human knowledge that this particular system is giving that kind of an output?
So I would say the real reason is it doesn't have a physical grounding, right? So it's not taught physics from ground up.
Mm-hmm.
For instance, it's been taught on text models and like all kinds of images. You don't know if those images are actual three-dimensional objects and what would be their physical properties.
Right.
For instance, if you want to really design an aircraft wing better, you want to ask about fluid dynamics, like what are the Navier-Stokes, those equations in terms of how fluid flow happens. You want to be able to look at materials, are they stretching as you fly this aircraft? Right. So those aspects have been traditionally done in numerical simulations. This is not entirely new. There have been computational simulation systems that can simulate how an aircraft would fly, but that's not been done with AI traditionally. Right. On the other hand, AI systems do not have this understanding, and this is something I'm working to bridge that gap.
Right. That's interesting. As a side to this is the Sora language model, or rather you call whatever AI model it is. So is this good enough as a product that can be gone into a commercial use status right now from what language training it has gone through?
Yeah. So the Sora model is a video model. It's been trained on all kinds of videos, including rendered videos, right? And that's why you see that quality in the demos where it's kind of you're zooming into a scene, like what you see in many video games, for instance. So in certain applications that could certainly be useful for people to reduce all the effort that it takes to create animations, but it still doesn't have full physical validity. If you see, for instance, the teacup and like how the fluid is moving, it's quite uneven and not how in the real world it would move. And again, that's the same reason, because it doesn't know that fluids are supposed to move according to this Navier-Stokes equation, for instance, or if materials stretch, we know certain models of what the plasticity is. So if we encode that and we build systems that can really simulate based on that, then we have physical validity. And that's something I'm working on.
Right. So I just want to expand this into a debate that's happening between Jeffrey Hinton and Gary Masters. I'm assuming you're following it.
Yeah.
So where would you take I wouldn't call it taking a side, but how do you synthesize these two sides? Because clearly one side is saying this is not good enough. The other side is saying that it's going to take over the human race. Mm-hmm. So where's this going?
So I think there is certainly a middle ground. And first of all, this aspect of AI just taking over the world, AI doesn't have agency, right? It's not sentient. It's something that we humans very much control, and it's just science fiction, anything beyond that. The aspect, of course, in terms of like the shortcomings, there are a lot of shortcomings with the existing models, but I think many of them can be solved. You talked about superhuman AI. We actually have that today. If you ask about what should be the weather tomorrow, most likely, you can take a guess maybe in typical conditions, you get lucky and it's correct. But if you really ask, will the hurricane or the cyclone, will it make landfall? I mean, we have no idea, right? We can just keep looking at this hurricane.
Right.
We can't really predict how that evolves because that requires the fine details in terms of how the fluids flow to predict the path of the hurricane. And we trained the first fully AI-based weather model based on all the historical weather data that is able to predict how hurricanes evolve. And in fact, in one of the hurricanes last year, the AI model was able to predict it several days earlier than traditional weather models were able to do so. And not only that, this model is tens of thousands of times faster than what you can do with numerical weather models. So what used to take a big supercomputer to run weather forecasts can now be done on a local desktop. So we've open sourced the code. So you could perhaps go and run your own weather model.
So this is available for people to go ahead and use it?
Yeah, it's fully open source. It's permissive. We were the first to open source this. So this is widely available. And many regional agencies are making use of this model. For instance, in Taiwan, they're using this model to further refine for the local weather conditions. And I think this can make a big impact, especially in in parts of the world where there isn't a lot of satellite coverage and there isn't a lot of, big supercomputers to run weather forecasts. You could use the power of AI models to be able to improve that. And so that's an example of a model that understands the physical world. And in this case, because it's trained on all the historical weather data, it understands both typical weather conditions, but also extreme weather events like hurricanes. But the important thing is because it's so much faster, first, of course, it's democratization. You can have people around the world use it. The other important thing is you can also predict extreme weather events with a better risk assessment capability. So there is right now a big cost factor to do that with traditional weather models. And now with these AI-based weather models, the cost just comes down tens of thousands of times. So you can predict extreme weather much better and also plan for those risks as climate change is going to be a big factor.
Yeah, I think that's part of the TransformX that the AI labs are working on, which is definitely something I'm going to come to. Before that, I just want to get that. So you've been straddling between academia and the industry. Like it's been a regular revolving door sort of thing. And finally, I think you moved to academia for good, or not sure what's the whole thing. But how do you see R&D developing between these two places, right? Because you've gone through like 2 decades in both the segments.
Yeah.
Is one thing catching up with another, or there's a change in the way they approach research? Could you give some sense around that?
Yeah, certainly. When I started working on AI, after I went from IIT Madras to my grad school and was graduating with my PhD, the notion of an AI scientist in industry didn't exist. Right? Those jobs just didn't exist. I could become a software engineer, and even though I enjoyed software, I really wanted to work on AI, and then academia was the only option. But then as deep learning was taking off and there was the need to build AI infrastructure, I went to Amazon Web Services, and that's where I helped build the AI team right from very few people all the way to almost 1,000 within 1.5 years. So seeing that fast growth to build products like AI training platform like SageMaker and many of the first vision and language APIs in the cloud, and also showing the power of cloud in terms of what it can do in many different areas. So when I joined Caltech, I was already at Amazon. And so it was kind of like having one foot in both directions. But coming to Caltech through that meant like I was able to, help with cloud credits and help projects across the campus. So, I could kind of see that there is a lot of potential for AI in different areas of sciences. And that's how I was able to really understand that, there is the need, for instance, for AI, everything from weather forecasting to creating better drugs to understanding like earthquakes, all kinds of very different problems, but they're mathematical underpinnings that unify them. And we can use that notion to also train AI models to have better physical understanding and solve these range of problems in science.
Right. So how does also Microsoft and I think Google, they do a lot of these academic research and some of their grants also doesn't have any strings attached to it. Do those kind of research help kind of enhance academic R&D, or how does it in the industry academia collaboration evolving?
Yeah. I mean, in my experience, the roles I've been part of, like where I could do open research, at NVIDIA, for instance, and really collaborate, that makes it very synergistic, right? So everybody benefits from that. So what you see in academia, especially at a place like Caltech, is a lot of those deep expertise in scientific domains. And the big tech typically doesn't have it, but then there's engineering and scale and GPUs, and that combination can create magic. And there are new ways to kind of scale that, and I'm exploring that now.
Wonderful. And how do you see that in the context of India? Like, is there a scope to widen these kind of research opportunities into the Indian area in terms of talent and infrastructure? How do you look at India as a place in terms of AI's use in development and research?
Absolutely. I think India can be a big leader in AI by making the right investments, especially at this time. So I was earlier at the IIT Research Park, and Professor Junjunwala has been a mentor from back then. And, so just seeing him be part of this research park and really having so many companies that have been successful here, and having everything from like rockets to like for disabled, exactly, and the vehicles for disabled and like kind of people with mobility issues. All of these very wide range of like startups that are forming there shows like how much talent is available here, and channeled correctly can just lead to such big gains. So I think one thing that's so important now, especially in the AI domain, is to invest in AI infrastructure, data centers with GPUs that can really be shared both for academia as well as industrial research.
Wonderful. So when we speak about infrastructure in terms of AI, data centers is a very important thing, as much as also I'd say the GPUs. And these GPUs are quite expensive. How ready are either organizations and academia in terms of building these kind of infrastructure for AI? Because fundamentally, for instance, if Microsoft has put $10 billion in OpenAI, that's a significant amount of money, and it's going into chip building and development. How does that fare in contrast to what's happening in India or any other country which is on the similar emerging economic status?
Yeah, I do think that is a worry, like in terms of like creating a big inequity in terms of GPU access, right? And that's where, you cannot expect just a local startup to, for instance, invest big in GPU resources. But as a country, there can be that focused investment and ways to then ask, who are the people who can access these resources, whether you have a grant proposal, similar to funding, now you have proposal for accessing these resources. So the best ideas can really make use of these large scale compute to, develop models that are especially beneficial to the local issues here, right? Whether local languages, but also local medical data, that can only be done in India, and that requires GPU access, at least any model that can be done at scale. So that's very much timely and important, right? So not to delay those kind of investments. And at the same time, necessity is the mother of invention in academia. And so, even at Caltech, we don't have a lot of GPU resources, but what we do have are smart students and researchers who are thinking about how to make these models be trained on lower number of resources. So for instance, one of the models we developed could reduce memory of these models by more than 80% during training. And we could fit like a Llama 7B, which is one of those popular meta models, into a consumer GPU, which is much easier to obtain rather than the bigger memory GPUs. So that's just one example of how, simultaneously as these models are getting scaled, research is asking how we can make these models be a lot more efficient to train, to do inference, and hence democratize it much more.
On that note, I want to go back to your the Trinity of AI talk, and the one that I actually listened to was the ACM one that the lecture that you gave. The very interesting point that you mentioned about, to the listener, this is something that I'd like to share, is that you should take your time to listen to Dr. Anima's TED talk on the Trinity of AI to get a little more idea around this. On the Trinity of AI, you point out about the priors where the action, or the place where you're focusing your research on. Could you give a sense on a slight overview about the Trinity, and then just get on to that point of how that robustness is getting built into the system?
Yeah, certainly. So to me, like, the Trinity of AI was something we coined when I was at Amazon Web Services, right? So because that was the beginning of the revolution of large-scale AI. And so large-scale AI requires lots of data. And now we see this growth in the data these models are trained on. So ChatGPT is trained pretty much on all of the internet, whereas the early models were trained on very small data sets that were doing only one specific task. For instance, you wanted to recognize just the sentiment in text and not anything else, compared to just learning everything about the text models. And so that's where we see the growth of data, but also growth of the compute as well. So like I mentioned, around 2010, when GPU started getting used for AI, how did that happen? It's not like the researchers had to program everything from scratch. So the CUDA, which is also a big aspect of what makes NVIDIA so successful, is the programmable ability to do all kinds of linear algebra operations. So back when CUDA was developed in the early 2000s, that was not AI, right? So, but it was linear algebra. So matrix multiplications are just broadly useful. And the idea was, let's build these basic operations and make them be highly efficient on hardware, be highly parallelized. And that aspect has now been used in AI. And now you see from GPUs just being, something that you could do small AI models to one that is like 1 trillion parameters for ChatGPT. So we're talking about tens of thousands of GPUs being used potentially at the same time to train these models. And that scale can even grow further. That's where, a lot of the aspects of what scale can do, we are pushing the limits.
And is that also why you also push for tensor algebra? Of course, it's a little, I think, out of the zone topic that, it's not usually discussed. The push that you talk about, multidimensional way to look at data, particularly video also as a space-time phenomena. What would be the next frontier in AI in that context? Because we don't have the kind of hardware to kind of do this kind of computation right now. That is, so that there's a significant runway there for that to catch up in terms of how the hardware will come. And second is also the development of model. So could you give a sense on the next frontier for AI in that context?
Yeah, so when it comes to tensors, they're extensions of matrices. So what you can do as matrix multiplications, you can now imagine that now instead of matrix as a square, now you can have a third dimensional tensor as a cube, right? And you can multiply it along different dimensions. And so there's a lot more processing you can do. But it turns out actually GPUs are great for tensors. And in lots of ways now, even NVIDIA and other people are extending operations with tensors that can be done efficiently on GPUs. Because there's even a higher degree of parallelism when it comes to tensor operations, because it happens in more dimensions. And that's the aspect that I feel many of the AI models are only beginning to exploit. The aspect I mentioned about saving memory costs, with tensor algebra, we can save it to an even bigger extent. And so these algorithmic aspects to further make the models more compact, more efficient, more, both energy efficient as well as being smaller, so they can fit in smaller GPUs, or even edge devices. If you want to run this on a drone or a sensor, you can't have a large model, right? You have to miniaturize that. So that's the next revolution that's beginning to happen, because scale cannot solve everything. Scale may help us learn what we call pre-training, like we can learn a lot of knowledge with scale, but ultimately to run these models, you may want to bring them to small devices.
Right.
And also during training itself, you may want them smaller because you cannot afford such a big cluster.
Right.
So both these aspects are, I think, the next wave of AI.
Yeah, it's going to be interesting, and also about the AI lab that you're building in terms of the climate model and other areas that you're focusing on. How are these in the domain of open source, and how are people using it? What do you see the future of these kind of platforms as they start emerging?
Yeah. So the AI model that I mentioned for weather ForecastNet that we created more than 3 years ago, that was the first fully AI-based model. And at that time, there was a lot of skepticism because people thought, well, there's decades of work that has happened on weather models, right? And that has no AI in it, and that works pretty well. So why replace this? But we came with not only the accuracy being good, but also the cost, like being tens of thousands of times faster. So that really provides now a showcase of what these models can do for different areas of science and engineering. As another example, we created a better medical catheter. So AI designed an optimal way to improve this medical device, a catheter, which is a tube to draw fluids out of the human body, but it's also one of the biggest sources of healthcare-related infections in hospitals. And what we did was to go to first principles. So understand that the fluid flow, how that happens is the bacteria can swim near the wall because there is less friction, like it can swim upstream against the fluid flow. And we were able to create these ridges that we could 3D print to create vortices to prevent bacteria from swimming upstream. And then AI was able to understand this whole physics of fluid dynamics and optimize and generate the best design of what would be the catheter.
So it turns out that AI can learn physics.
Yeah, and AI can not only learn physics, it can design based on that. And we only had to 3D print it once, and we measured 100-fold reduction in bacterial contamination. And to me, that is the bigger revolution as well waiting to happen, what it can do in the physical world and in traditional engineering and manufacturing industries. So what would earlier require a lot of physical testing, so you would have to go test it. If the design doesn't work, go back to the drawing board, or you try to do expensive simulations, but you can't generate an optimized design based on those, simulations. You have to go to the physical world. What if you could accurately model that in the virtual world? And AI can make this so much faster. For instance, as another example, we worked with UK Atomic Energy Agency to train on data of plasma and nuclear fusion. How does the plasma evolve? When does it become unstable and the nuclear fusion is no longer happening, right? So that's a big drawback in terms of making nuclear fusion practical. And of course, if we made it practical, this would be such a clean source of energy and one that would really solve a lot of the issues with respect to climate change. And AI is now helping us understand these kind of very complicated physical processes and doing that 1,000,000 times faster than what you could do with traditional simulations. So that ability to understand the physical world, reason, design, and come up with better candidates than what was possible can really help us also tackle many of the engineering and science problems that have so far been hard for AI.
Wonderful. So it looks like to me we would be the generation that will see the artificial intelligence knowledge kind of surpassing the human intelligence. Is it fair to have that as maybe the future? Maybe by 2030 or 2040, I think we should be getting into an AGI zone, or even earlier than that.
So, yeah, I find it hard to make an exact prediction because how we measure AGI is itself a hard question, right? So because if you ask about AGI in terms of common sense, these models like ChatGPT are quite lacking in that. And especially if this is an AI model and you can fool it, you can quite easily kind of have it trip up because it just kind of goes off ramp very easily, at least with the current design. On the other hand, something like the weather model or designing this catheter or understanding plasma Humans are nowhere able to do this, right? But we use other computational tools today to do that. And that is being replaced by AI, making that so much faster, tens of thousands of times faster and cheaper to run, but also being able to come up with new design candidates that humans are not able to conceive. So in that sense, AGI is already there in those instances.
So I think we clearly have a bifurcation of roles here on things what AI is going to accomplish and what as humans we can do. So we will continue to be the kind of guidepost to AI to say, these are some of the areas that we want you to do some work in. So get it done for us. And these kind of optimizations are going to significantly advance in future, where you're going to see a lot more large-scale machine learning automation happening.
Yes, absolutely. Humans are still giving the design guidance or saying, oh, these are the design constraints. This is how I want it to work in the physical world. And then AI is able to design that. But we'll also see these models get broader, and this is what I'm working on. Instead of having a model narrowly understand only weather or only this nuclear fusion of plasma, can we have ultimately a model like ChatGPT, but for the physical world? One that broadly understands different areas of physics, is able to simulate and design. And the benefit of that is being able to come up with all kinds of multi-physics simulations. So think about, again, going back to the example of the aircraft wing, it's not only fluid or aerodynamics you want, but you also care about the material, what is the right material to design. And you also care about like noise, for instance, what is the noise characteristics of this. So you need, like in the physical world, very complex kinds of models that need to come together for design. And these aspects, we can have AI that understands broadly multiple areas to be able to solve.
And in terms of the ethical aspects of it, if you're looking at an entire system of AI coming into play, how does ethics kind of find its way into these kind of reasoning? Primarily, I'm also going back to the time when you actually pointed out the Amazon's recognition tool had its own AI biases. So what kind of built-in ethical methods are going into these kind of systems?
Yeah, and that's a difficult task, but it depends on the system. If it's a narrow system like face recognition, and back when I was concerned about that, there was certainly a bias in terms of data not being representative of all demographics, and especially the darker skin tones not being having sufficient accuracy in these systems. And since then, a lot has changed, and these systems have become better because they have access to wider data sets and are more carefully trained, because you're looking at these fairness metrics of how well they do on different populations. But what is now hard is, what about systems like ChatGPT that is quite general, right? So how do we measure bias in these systems? And there's not one value. I mean, should it be like biased in terms of, for instance, health related questions? Because indeed, if different genders and different races have different outcomes in certain cases, we need to be able to have that. At the same time, you don't want undesirable biases and ones that are stereotypical and harmful, for instance, during hiring or other kinds of filtering. If it's done automated way without human supervision, this can be a challenge. And how do you monitor those use cases, and how do you really ensure that careful testing is done? And I think that's the difficult part, but I think the regulation should only be at these downstream, even though it's difficult. Because if many countries and many organizations are trying to regulate and limit what can be trained, but the worry is, those just again create further barriers in terms of democratization and in terms of open sourcing these models with broad benefits to humanity. On the other hand, it's what happens in the downstream applications that matter. Right? So if you're using ChatGPT for hiring, that's a very different use case from asking it to tell some jokes. So you don't want to regulate all of them. And I think especially in a country like India, where there's just so many diverse use cases, it's very important to be, focusing on the growth and development and not risk having over-regulation.
Right. Thank you. Thank you so much, Dr. Anima. I think that was a fantastic set of interesting points that you raised, specifically around how AI is being developed and what are the various ways in which the community is developing applications around AI. Thank you so much for your time, Dr. Anima. It's a pleasure having you on the interface.
Yeah. Thank you, John. And it's great to do this here in India and in IIT Madras. Thank you.
Thank you for tuning in to the Interface podcast. I hope you like this discussion. For more such episodes on technology and innovation, tune in to the Interface on Spotify, Apple Podcasts, or wherever you get your podcasts from. Do share your comments with us at the Interface at thehindu.co.in. To keep yourself updated with the latest tech, please go to thehindu.com or follow us on all social media platforms. Thank you.